Have you ever pondered the life and death of stars, those celestial bodies illuminating the night sky? Our journey begins with the birth of a star. Picture a vast, cold and dark cosmic cloud, a nebula. Nebulae, the nurseries of stars, are abundant in our universe, filled with cosmic dust and gas. Over countless millennia, these particles are drawn together, bonded by the omnipresent force of gravity. However, the birth of a star doesn't happen with a mere gathering of cosmic dust and gas. An external catalyst is necessary to set things into motion. This could be a shock wave from a nearby supernova or the gravitational pull of a passing star. These forces can compress parts of the nebula, triggering the gravitational collapse of the dust and gas within. As the materials in the nebula collapse under gravity, they form a dense, hot core. This core, or protostar, is where the magic happens. As it continues to attract more and more matter from its surroundings, the pressure and temperature inside the protostar rise dramatically. Now we must remember that stars are essentially gigantic nuclear reactors. When the temperature and pressure at the core of the protostar become high enough, nuclear fusion begins. Hydrogen atoms are squashed together under extreme conditions, creating helium and releasing a tremendous amount of energy in the process. This energy pushes outward, counteracting the inward pull of gravity and maintaining a delicate balance. This process of nuclear fusion ignites the protostar, and voila, a star is born. The energy it emits lights up the surrounding dust and gas, creating a glowing spectacle that we recognize as a star. It's a cosmic dance of forces, a stellar ballet choreographed by the laws of physics and performed on the grandest of stages, the universe. So that's the birth of a star, an event that's been repeating itself for billions of years, creating the myriad of twinkling lights we see in our night sky. Just like every living being, stars too have a humble beginning, born from the cosmic dust and gas. After the birth, stars embark on a long journey of shining brightly in the cosmos, but how exactly do they achieve this radiance? Well, let's peel back the layers of a star and take a look at its beating heart. The secret lies in a process called nuclear fusion. Imagine a bustling city, but instead of people, it's filled with hydrogen atoms. These atoms are in a constant state of motion, colliding with each other at high speed. When they collide, they fuse together, forming helium. This fusion process is like a grand celestial dance where every step releases vast amounts of energy, making the star shine brightly. Now you might be wondering, why doesn't the star collapse under its own weight? It's as if a balloon filled with helium is trying to rise, but a weight is keeping it grounded. In a star, this balance is maintained between the gravitational pull, which is trying to collapse the star, and the outward pressure from these fusion reactions pushing against the gravitational force. This equilibrium, this perfect balance, is what keeps a star stable and allows it to shine for billions of years. But it's not all smooth sailing. The star faces many challenges in its luminous life. One of the major ones is fuel depletion. Just like a car that runs out of petrol, a star too starts to falter when its hydrogen fuel begins to run low. But it doesn't just fizzle out. No, the star fights back, trying to fuse heavier elements, creating a complex, layered structure within its core. This battle between gravity and fusion, the struggle for balance, the constant dance of atoms, is what makes a star's life so fascinating. It's a cosmic ballet, a symphony of celestial forces, playing out over billions of years right above our heads. The star continues to shine, perfectly balancing the forces within until its fuel starts to deplete. And that's when we enter the next phase of a star's life, a phase that's as dramatic and breathtaking as its luminous life. But that's a story for another time. What happens when a star exhausts its nuclear fuel? Does it fade away quietly, or does it exit with a bang? This is where the Stellar Swansong begins, the final act in the life of a star. As a star ages, it burns through its hydrogen fuel. This phase of a star's life is akin to a ticking clock, counting down the moments until the hydrogen is depleted. But the star doesn't simply fade away. No, it goes out with a flare, a final, dramatic transformation. Once the hydrogen fuel is exhausted, the star's core contracts and heats up, igniting the next element on the periodic table, helium. It's a bit like swapping out an old spent candle for a fresh one. The star now begins to burn helium, but This is no ordinary flame. The heat and pressure cause the star to expand, ballooning out into what we call a red giant. Imagine a star, once a pinpoint in the night sky, swelling to a size that could swallow up planets, but the helium fuel, just like the hydrogen before it, won't last forever. As the helium is consumed, the star's outer layers begin to cool and drift away, a process that paints a picture of cosmic beauty. This drifting material forms what we know as a planetary nebula, a cloud of gas and dust that glows with an ethereal light. It's a celestial farewell, a final masterpiece painted by the dying star. As the outer layers continue to drift away, the star's hot core is exposed. This core, known as a white dwarf, is all that remains of the once mighty star. It's a small, hot ember left to cool over the course of billions of years. The star's journey may end here, but its legacy lives on. The materials cast off by the star during its death throes will become the building blocks for new stars, planets, and possibly even life. The star's outer layers are cast off into space, leaving behind a small hot core. But in this grand cosmic theater, the end is just another beginning. Now that the star has shed its outer layers, what becomes of the hot core that remains? Well, the destiny of the core is an intriguing one, and it largely depends on its mass. Let's first consider a smaller core, roughly the size of our planet Earth, but with a mass similar to that of the Sun. This compact, dense core is what we call a white dwarf. It's like the ember of a once roaring fire, now glowing with residual heat. Over billions of years, the white dwarf cools and fades away, its final sigh a whisper in the cosmic wind. But what about larger cores? The story is quite different and a lot more dramatic. Picture a core with a mass more than 1.5 times of our Sun. The pressure is immense and the core can't withstand it. It collapses under its own gravity, leading to an event of cosmic proportions, a supernova explosion. This grand spectacle, albeit brief, can outshine entire galaxies. Now, once the dust settles, we're left with the heart of the star, its core. If the core's mass is around 1 to 3 times that of the Sun, the outcome is a neutron star. These stars are incredibly dense. A teaspoon of neutron star material would weigh about as much as a mountain on Earth. However, if the core's mass is even greater, say more than 3 times that of the Sun, even neutron degeneracy pressure can't stop the inevitable. The core collapses into a point of infinite density, a singularity, creating a black hole. These enigmatic entities with gravity so strong that not even light can escape are the ultimate celestial graveyards. So the stellar life cycle concludes with the remains of the star becoming a part of the celestial cemetery. Each core's fate, be it a serene white dwarf, a pulsing neutron star, or an insatiable black hole, is a testament to the star's life. Whether a peaceful white dwarf or a mysterious black hole, each star leaves behind a unique testament to its existence. The life and death of stars seem like a tale of cosmic proportions, but did you know that it has a direct impact on our existence? In the grand scheme of cosmic events, the life cycle of stars and our life on Earth are intrinsically intertwined, a connection that is as fascinating as it is profound. You see, the stars above us are not just celestial bodies that twinkle in the night sky. They are cosmic forges, responsible for creating the elements that make up everything in our universe. Stars are born from clouds of gas and dust, primarily composed of hydrogen and helium. But as these celestial giants mature, their intense heat and pressure ignite nuclear reactions in their cores. These reactions merge lighter elements into heavier ones, a process known as nuclear fusion. But the magic doesn't stop there. When a star exhausts its nuclear fuel, it meets its demise in a spectacular explosion, a supernova. This cataclysmic event not only marks the end of a star's life, but also the beginning of something else, something remarkable. The immense energy of a supernova explosion propels the newly formed elements out into the cosmos. This star stuff, dust enriched with elements heavier than helium, is then scattered across the universe. Over billions of years, these particles coalesce to form new stars, planets, and yes, even life. That's correct. The very elements that make up our bodies, the carbon in our cells, the oxygen we breathe, the iron in our blood, were all forged in the heart of stars. We are, in the most literal sense, made of star stuff. So, when we talk about the life and death of stars, we are also talking about the story of our own origins. Our existence, the existence of our planet, and indeed all life, is a direct result of these celestial events. So, the next time you gaze at the night sky, remember we are all made of star stuff, born from the life and death of stars.